Okay, good afternoon. Is the podium mic? Good afternoon, and welcome to the 2013 Distinguished Lecture Series at ICCAD 2013, sponsored by the IEEE Council on Electronic Design Automation. It is my great pleasure today to welcome Dr. Lars Liebman from IBM. Dr. Liebman has a background in engineering physics, works mostly on the interface of design, technology, co-optimization, and today will be telling us a little about the future of the technology on which all of our industry ultimately depends, lithography. Please welcome Dr. Lars Liebman.
Yeah, thank you, Joel, and thanks to CETA for inviting me to come here. I have my timer set to 45 minutes, but honestly I have no idea how long this talk actually takes. So this is when you earn your lunch, right? You've heard the expression, no such thing as a free lunch. So Kathy, lock the doors. We're here for the long run. So yeah, this is basically a little bit of background on lithography as it has evolved over the years. Hopefully some of you have been exposed to some of the kind of side effects of lithography. And when I was putting this together, I thought, why am I doing this? I know why you're here, right? Hey, it's lunch, right? You got to eat. What do I want to get out of this? So I thought, I might as well put this onto the opening slide, right? Lithography has been working, very hard, and it'd be good to get a little bit of sympathy for our pain from the design community. So maybe if I share with you a little bit of how far we're bending over backwards to keep technology moving forward, you might appreciate some of that. But so more seriously, I think there's a growing need to collaborate between design, EDA, process lithography in an early engagement, in a very sort of deep engagement that we sort of mutually understand what problems we're actually trying to solve, and then with a level of honesty, right? Going to some big fabless customers, sometimes they want to engage you early, but they just want to kind of beat you into submission to accept their designs that you have no idea how to manufacture. So that's not the kind of collaboration I would like to see. There really has to be some give and take, and I think that's best done by understanding kind of the physics behind the challenges. And then finally, I think there's still some hope for us as a community to take some of these restrictions as they're evolving and turn them into a positive thing. Joel and I were talking about transistors. As you go from sort of the good old days where you had sort of an infinite variety of transistors in width and length, and now we're down to you get maybe one, maybe two channel lengths. If you really beg, and you get maybe a 2-fin device and a 3-fin device, and that's the entire spectrum of transistors you have. Maybe there's some opportunity to fundamentally improve how you approach design and not just treat it as a restriction. So as we go through all this material, maybe that'll spark some creative thought, and please put me on as a co-author in whatever patents you file as a result of this presentation. The outline, I put together sort of everything you need to know about lithography in one slide. I don't know, Rosetta Stone. Maybe that's a good name for it. You can be the judge. Then, as we traverse sort of the history of lithography, as we go through the different fundamental resolution limits that we have tackled and conquered, we'll look at how those drove different levels of design restriction. And the main point here is, it's not just the process people being lazy or evil. There is a fundamental reason for each one of the design restrictions that has been imposed over the years. I'll spend quite a bit of time on double patterning, and I think the brightness of our projector far exceeds the brightness of the pointer, so I'll wave it around just so I have something in my hand, but I don't think you'll be able to see anything. Finally, there is life beyond double patterning, and at that point things really start to get interesting. So please stick around long enough to get to that final bullet, because that's the really interesting part. All right, here's everything you need to know about lithography, all crammed into one slide. You know, the good thing is it's all in one slide. The bad thing is it takes about 3 hours to explain what's on the slide. So don't try to absorb it all at once, right? I don't want to cause any indigestion here after the big meal you had. But I'll just give you a quick overview here, and then I'll step through this fairly slowly. So across the top, I don't know, pointer's useless. Maybe this will work. I don't know. So across the top, I have the different technology node names. The names have become more standardized. What the node really means has not, but we're sort of on this cycle of scaling the node name by 0.7 and rounding it to the nearest integer. That's sort of the closest I can figure out, but it has nothing to do with any kind of physical dimension in the technology. So as a lithographer, you kind of classify the technology by the minimum pitch that has to be resolved, and typically it's one of the 1x wiring pitches that forms the minimum dimension. So that's the second row here. Then I have wavelength. It's not a very exciting field. It's all 193 nanometer light, and of course that's quite central to this whole talk, and we'll talk about that some more. The numerical aperture, which is the second big resolution knob in lithography, right? You can see how that is increasing. And then down the diagonal is this the Rayleigh factor, right? The K1 factor, which is sort of the central parameter to lithography that really measures how difficult the resolution is, right? The smaller the number, the harder your lithography team is working, and we'll talk briefly about how that is mathematically related there. On the left side, I then have in sort of colors of increasing level of alarm, right? I hope I conveyed sort of how it gets more difficult as we go from white, green down to black. The different resolution domains, right? And these are not arbitrarily picked. They have a physical background. And then over on the opposite side of the table are the resolution enhancement techniques, or the computational lithography tricks that we have implemented to overcome these resolution limits. And then finally, across the bottom are sort of the design implications that all of this leads to. But let's take it one step at a time. So starting in the domain where lithography was, quote unquote, easy, the basic resolution, as I already mentioned, first of all, lithographers measure resolution for reasons I still can't quite understand in half pitch, right? So the center to center spacing of a feature divided by 2 is the critical dimension that we quote resolution in, and that's given by this Rayleigh constant times the wavelength of your illuminator over the numerical aperture of your projection lens. And I drew a nice little cartoon here, right? So you have light coming into your photomask. That light has a certain wavelength. The photomask acts essentially like a diffraction grating, right? It throws diffracted orders of light out at a certain angle, and you can see where these diffracted orders interfere. And then the job of the projection lens is to capture the light and project it down onto the wafer. And the numerical aperture simply measures the largest diffracted angle that the lens can still capture and form an image out of. And so now you have various parameters you can use to scale your resolution. Right, one is to go to a larger numerical aperture. Right, the higher the numerical aperture, the further you can diffract light out and still capture it. It's a somewhat problematic scaling parameter because it gets kind of difficult to make lenses at a numerical aperture significantly larger than 0.5. And the depth of focus, the range over which you have to control the planarity of your image, or the depth of the image, scales as the inverse of the square of the numerical aperture. So as every time you increase the numerical aperture, you lose your depth of focus, and you have to put better focus control measures into play. This K1 factor, of course, if you learn to operate at a smaller K1 factor, you get your resolution down. But there, as will become very clear as I go through the rest of this material, yield, cost, complexity, everything starts to get affected at a K1 less than 0.65. So for many years, the main parameter with which we scaled resolution was the wavelength of light coming out of the illuminator, being diffracted here by the mask. These are all wavelengths where you can't just simply turn on a light bulb, right? They're sort of discrete lines and then laser emission, so they're fairly discrete steps between available wavelengths. And we kept scaling merrily along, and the idea was always to get the next generation of exposure tool just in time, so that that your resolution doesn't get too challenging and you can keep up with technology scaling. And all of that worked fairly well until we got to 193. Any wavelength beyond that was essentially taken off the roadmap. 157 was supposed to come online as the next wavelength, and there were various issues related to the materials properties of the optical elements. Right, everything had to be manufactured in calcium fluoride. Optical quartz was no longer good enough to transmit light. There were some problems modeling that accurately in the early phases, and in the end, the industry as a whole sort of backed away from that whole proposition. And then 126, at this wavelength, you basically have to operate in complete vacuum, right? Everything absorbs 126 nanometer light, so you have completely reflective system in a vacuum. And then people said, if we have to do all of that, we might as well go to X-ray radiation and not do any more optical lithography. So 193 was the last optical wavelength that we had, and that sort of set things in motion that what we now call computational lithography, basically playing tricks to enhance the resolution based on operating at a lower K1 factor. So that takes us through this out of the white domain where things were kind of boring. And we're now operating in this range of K1 factor less than 0.6, 0.65, right, where I said things get kind of difficult, down to the resolution limit of conventional lithography, which is a K1 factor of 0.5. And in that domain, the design impact wasn't that severe yet. But this is when we started to have conversations with the designers. And I should pause here for a moment and acknowledge Andres. First of all, put your cell phone away. I mean, what are you checking your messages here? This is crazy. No, sorry. Andres and I put together a tutorial on lithography a couple of years ago, and I shamelessly lifted some of these background slides from that tutorial. So Andres ran a lot of these simulations at the time, and they were just so beautiful. I felt that I should give them another chance to be shown here. So thank you very much for, not that you gave me permission because I never asked, but anyway, you go back to updating your Facebook status then. All right, so just to briefly illustrate what happens in this domain as we approach the K1 of 0.5, right? At a large K1 factor, the diffracted orders are such that the lens can capture a whole bunch of them, right? That you have plenty of information making it through the lens. You can make square corners and all your edges are perfectly straight. And whether you're an isolated feature or a nested feature, you still have an abundance of diffracted orders, so the images don't really vary as a function of proximity. As you approach the K1 equals 0.5, which is the exact point at which the first and minus first diffracted orders just barely make it through the lens, right? So now you're forming an image with just one diffracted order. At that point, your resolution sort of really degrades, and the phenomenon you see is that features of various proximities get different intensities, right? The more isolated you are, the more diffracted orders the lens can capture, and the more nested you are, the fewer diffracted orders there are. So there is a difference in dose as a function of the proximity of the environment that this feature sits in. And you can see this in these simulations that based on the neighborhood of features, you get these inaccuracies, these proximity effects. And the one good thing is that they're very systematic, right? You can calculate exactly how these things behave, and that's what led to the introduction of optical proximity correction. And we basically built mathematical models of how features are distorted on the wafer as a function of these diffraction effects. And while we were at it, we threw in some other effects like what happens on the mask making, what happens in etch, and sort of captured all the systematic process inaccuracies. and then essentially pre-distort the mask image, right? We take this layout image, and we add these distortions, these decorations, you know, edge biases, line and serifs, and so on to them, so that by the time we go back through this process, we get an image that more closely resembles what the designer had in mind. Now, there's no way to get square corners back, right? That information is lost. There is not enough information being transmitted through this essentially low-pass filter to make a square corner, but you can make the rounded corner in a place that's more you know, functionally equivalent to what the designer had in mind. And all of this happens, of course, on the fab side. Designers are not affected, but you know, much like the invention of the parachutes closely followed the invention of the airplane, we came up with this idea of litho-friendly design, just kind of, you know, cover ourselves whenever optical proximity correction didn't quite work out. So the idea here is that what I'm showing here is you know, some polylines crossing a diffusion. You see these landing pads with vias on it, and then these blue bands are the variability bands. That is sort of a statistical prediction of you know, the range of shapes that these patterns can assume. And you can see that whenever we have these landing pads, we get you know, corner rounding, of course, right? We can't make square corners. And then because of the correction, there's a little bit of overshoot, some pinching here. But in general, this image, as predicted by these contours, will work, you know, quite adequately. But then every once in a while, there is a situation where this whole situation is just over-constrained, right? So you can see this landing pad has a very high aspect ratio. There are features both on the left and right to this, so that you can't really compensate too much for this overshoot. Otherwise, you'll start bridging to the neighbors. And the result of all of these variables is that you get a pinching error here. And rather than coming up with 100 different design rules that describe the bad situation versus the good situation, we said, just follow a basic set of design rules, run this litho simulation, and essentially treat it like design rule checking, right? That we assign a fail limit to the contours, and if you reach that fail limit, then you have to fix your layout. And then, in principle, that worked quite well. It took several more technology generations before this found any kind of broad acceptance with the design community, I would say. But this sort of set that all in motion, that we had these models available to capture these systematic effects. And it made a lot of sense to provide these models to the designers rather than having overly restricted design rules. So that was the advent of litho-friendly design. There are no horizontal surfaces anywhere in reach of me to put a glass down. So if I disappear below the podium, that's just to get some water. Don't worry. All right, so that got us then into this range, where we were getting to 0.5. But I said, that's a hard resolution limit, right? That the diffracted orders no longer make it through the lens, right? What are we going to do? Of course, that didn't stop us. We came up with a very smart solution. I use the term "we" very loosely, as some genius out there had this idea. It wasn't me. I can't take credit for this. I just make the PowerPoints here, right? So basically, we had this situation that at a K1 of below 0.5, right, the diffracted orders miss the lens, somewhat catastrophic. You're no longer forming an image. You only get the 0th order. But the only thing that tells you is sort of the average pattern density on your mask, right? So if you have equal line space gradient, you get 50% light through. There's nothing you can do with that information. But if you then tilt the illuminator sort of on its side at just the right angle, you can actually form an image with the 0th order and the 1st diffracted order. And because that angle, right, the angle between the 0 and 1st order is half the angle between the 1st and minus 1st, you actually double your resolution. Right? You can now get to a K1 of 0.25, where before we were stuck with a K1 of 0.5. And this is of course fantastic. We bought ourselves a couple of technology nodes out of that simple trick of tilting the illuminator on its side. And furthermore, it's quite easy to calculate what that angle should be, right? You're just recentering the diffracted orders. So you can calculate the angle as a function of the wavelength of light you're using, and we by now all know it's 193, right? So I could just replace that lambda with 193, and then you divide it by the pitch. So now you know exactly what the angle is, but you also see immediately that this only works for one pitch. So if you're maybe a memory manufacturer and your entire design consists of one, kind of grating, you're in good business. For most other designs where you have a range of pitches to take care of, you have the problem that this trick, really sort of degrades in its effectiveness as your feature pitch deviates from the pitch for which you optimize this off-axis illumination angle, and that's kind of shown in this sort of sawtooth curve here, right? If you pick a feature dimension, for the tight pitches for which you optimize this angle, you have process window that's adequate as shown in this color scale, and it's probably a little reverse, right? That the good process window is kind of red, and then low process window means you're going to struggle with yield, is down in the blue. But you're getting to a pitch that grows, and now you cross this boundary where fab people no longer feel like they can actually manufacture this thing. So you would have to then put design rules in place to say, don't design there. We can't print this, or the variability is too high. But then as the pitch keeps increasing, you get to a point where you can insert this dummy feature. Right? We call these sub-resolution assist features, and they're assist features in that they try to mimic the pitch for which you set your illuminator, and they're sub-resolution because you try to keep the feature size small enough that they don't actually form an image on the wafer. So it's a little bit of a delicate balancing act that the feature has to be large enough to actually perform the assistance it's supposed to perform without actually leaving an additional line on the wafer. So you have these transition regions where the pitch is too large to survive on its own, but it's too small to put one of these assist features in, and that's where you get a steep drop in your process window, and then things recover a little bit. And then you play this whole game again where one assist feature is kind of not good enough anymore, but you can't quite fit two in there, and you get another one of these transitions. So you have this sawtooth. Things are no longer monotonic, right? There used to be a time when all you had to worry about was the minimum dimension, the smallest pitch in your design. That was the hardest thing to make. Now you can have features that are quite loosely spaced, but they're in this forbidden pitch region, and we still have no idea how to make them. So that had a quite profound effect. And up here is just another sort of cartoon illustration of if you do nothing, then the process window degrades, yield collapses, and then you keep inserting assist features as I'm showing here. What's more interesting to the design community is design rules, and all I did was I took designers from like the 1x metal level. In terms of the width of the feature you're drawing and the width of the neighboring feature, what are the allowed spaces? And basically, anything below 1x space was forbidden, everything above 1x space was allowed. No sort of fine print there. But as we went to off-axis illumination, because of this non-monotonic behavior, the design rules became incredibly complicated. And this is where then people were showing up at conferences with design rule manuals, to show how thick they are, and people were making extrapolations of, if the number of design rules keeps increasing by node at the same rate, we'd all drown in design rule manuals, and a lot of DFM startups were formed in this time frame. Because if you do a sort of linear extrapolation of this kind of increase in complexity over time, it really would have killed the industry. So a very, very distinct step, right? Once we went to off-axis, kind of a genius move, but then we had to deal with this non-monotonic behavior, and design rules really took a turn for the worse. Unfortunately, for a lot of the investors that invested in these DFM startups, things did not get worse at the projected rate. We got about 3 technology nodes, on this scale that I'm showing here, 3 technology nodes out of that level of complexity. And that, of course, was caused by the fact that sort of the hardware people stepped up, and they gave us significantly better resolution through the advent of immersion lithography. Right? Vern Lin, who started his career at IBM, and then he's now director of very important things at TSMC. He sort of pioneered this idea of putting a layer of water between the lens and the wafer. Kind of like you did in high school biology lab, right? When you're looking at cells, and you want to get better resolution, you dip the whole thing into water. Makes sense, when you're looking at frog lungs or whatever you're looking at. But you're doing this in a clean room, right, with very sensitive electronics, and I never thought this would work, but it did. And it extended the resolution for several technology nodes so that we really stayed flat in this domain of off-axis illumination. But then of course that kind of lithographication came to an end, and we had to step up to the plate again and do something new. And that something new has to do with sort of simple geometric constraints, right? I told you that the resolution limit of normal lithography is K1 of 0.5, then you tilt things on the side, now you can get a K1 of 0.25. Well, that was a bit of an oversimplification, right? Because the way we achieved this off-axis illumination, at least in the early days, was to simply stick an aperture into the illuminator that blocks all the light and only lets light out in these corners. Over time, that became more sophisticated, and we now use diffractive optical elements that actually redirect the light, because we can't afford to throw out that much light anymore. It's kind of expensive to make, and if you block that much light, it tends to heat things up and so on. So now it's a more sophisticated element, but it still does basically the same thing, right? It redirects light out in the corners. But the illumination angle, right, that we derived a few slides ago is not this radial angle. It's the perpendicular projection, right? So for all vertical features, it's this angle that matters, right? The perpendicular projection onto the vertical line. For horizontal features, again, it's that perpendicular projection. So you can see immediately there's this factor of square root of 2 involved in this whole equation, right? That you can't really get to 0.25 lambda over an A, because if you want to keep things symmetrical, you have to put your illuminators out into the corners where they contribute equally to vertical and horizontal features, but they can only do so at a square root of 2 times 0.25. So to get below, and square root of 2 times 0.25 is roughly 0.35, right? That's where that number comes from. Again, these numbers, they're not arbitrary. They have a physical reason behind them. So to get below K1 of 0.35, you have to deal with this asymmetry, right? One way of dealing with is, tell your designers you can only design one orientation, right? Vertical, horizontal, pick one. And for some levels that actually works, right? The poly level that forms your poly gates, we were quite successful convincing designers that all they need is one orientation. Now, there's this little detail that even if you design only vertical features, they have line ends, right? Which in this scheme would have an enormous amount of error. So the way we solve that is to just make continuous lines and then come back with a cut mask and form the line ends. So when we're saying single orientation, that includes line ends, right? So a fairly limited set of mask levels where that trick works. The other idea of, if the designers come back and say, first metal has to be bidirectional, I can't figure out how to make it unidirectional, we say, okay, well, do 2 exposures, right? It's just like, doing 2 exposures on a film camera. Some of you are old enough to remember those things. You put a layer of photoresist onto your wafer, you load your first mask, you expose all the vertical patterns, you don't move the wafer, you keep that there, you load the other mask with all the horizontal patterns, do that exposure, add them together on the wafer, and then continue your processing. And you can recover your resolution that way. But now you're doing 2 exposures. The other sort of trick is to kind of combine those 2 things, right? To do fancy illumination and have some discussions with the designers around preferred orientation designs, maybe not completely unidirectional, but say one orientation must be more important to you than the other orientation. And when you do that, you can come up with very sophisticated illuminators, right? That really sort of pixel by pixel calculate where you can put the light to get the best results. It's not a miracle solution. It doesn't give you more resolution like the introduction of a shorter wavelength would, but it helps you manage trade-offs, and that's what I'm trying to show in this table here, where if you have kind of a fairly conventional illuminator, right, where your light just sits out at these poles, again on the vertical and horizontal axis to really get to that full K1 of 0.25 and a fairly conventional mask, you can see that everything is sort of equally bad, right? Here we have horizontal lines and vertical lines, and those red bands indicate the variability bands, right? They indicate the level of uncertainty we have in the imaging. For this particular design, it works out to be 29 nanometers, so that exceeded our specification. Right? For two-dimensional features, you're printing nothing but garbage. Larger lines, sort of, larger pitches, make the cut. Isolated lines, again, exceed the tolerances. So now if you do a very sophisticated optimization in your illuminator, you can see here in the second row, right, the sort of pixel by pixel optimization, you can do some trade-offs, right, where now the horizontal lines have tighter tolerances than the vertical lines, and some of the 2D stuff is starting to take shape. But of course, you can't do this without actually having some conversations with your designers as to, hey, which orientation is actually important, right? What does this stuff actually do on the wafer, right? All lithography is polygons, and you really can't have sort of the useful optimization discussions here. So that's a very important point, right? That you have to have that communication. And then finally, if you do this very sophisticated mask optimization together with a very complex a very sophisticated source optimization together with very complex mask optimization, then you can sort of get the last few nanometers out of these trade-offs and get everything to be in spec. None of these features are sort of pristine, but they're all kind of within spec, just barely, and you avoid having to do multiple exposures. Now, the sort of fine print on all of this is that the fewer patterns you have to worry about, the more detailed the optimization can be. So this whole idea of construct-based design really came out of this idea of very detailed source optimization. So here's just a quick summary from some work that we did with Carnegie Mellon University, where in this case we were looking at the support circuitry of an embedded DRAM, and I guess it's a local interconnect level. And we looked at how many of these sort of 4-pitch by 4-pitch kind of shapes or constructs are in this design. And we started out with 133, and then the hard-working graduate students at CMU redesigned this thing and sort of got it down to same design, same functionality, but made up of only 55 of these constructs. And you can see the benefit over here in this bar chart, right? So here's the original 133 designs with conventional illumination. Then if you reduce the number of constructs, you already see a benefit, right? That some of this variability is caused by some of the patterns that you've just gotten rid of. But then it has an even bigger benefit if once you're doing source mask optimization, right? That you can get a 15% improvement in this variability by eliminating or reducing the number of constructs, then doing a very detailed optimization. So this is something that I think is still work in progress to this day. The idea of let's not argue over design rules so much, let's argue over what are the exact shapes you need to make your design, and how can we build design tools that think in terms of constructs rather than design rules. And I think there's still a lot more opportunity there, but it really helps the pattern community. All right, so that takes us then down to this K1 of 0.25, right, where we're completely off axis, and we've really reached another hard limit. Again, that didn't really slow us down. All right, we have to stay on this 2-year cadence, so there's no time to take a breather. So the next step we have to do, right, if you're at this limit of K1 0.25 and you keep pushing the resolution harder, you have a pitch that is below this K1 of 0.25. If you do double dipole lithography, right, just do double exposure, do the horizontal patterns into the resist and the vertical patterns. Since neither one of them is actually resolved, adding them together is just sort of pointless. You're just adding garbage to garbage, and you can see there's absolutely nothing resolved here. So what we have to do to push resolution further is kind of print half the patterns, right, at twice the pitch, memorize those, get rid of that photoresist, which is now expended, put on a new layer of photoresist, so to completely optically decouple those two exposures, and then print the second half of the patterns. And that, of course, is one of the double patterning techniques, we call litho etch for kind of obvious reasons after I just explained to you how we do this. And that takes us, beyond this resolution limit of K1 of 0.25. So, since I know many of you are still digesting here, I thought I'd sort of recap what we've just gone through. Right? So the 22 nanometer node, layout pitch is around 80 nanometers. So what I'm trying to do here, rather than making the layout smaller at every node, I keep the layout the same, and I'm showing you kind of what 193 nanometers, what the wavelength of light looks like relative to that layout. So keep an eye on this little red arrow as we progress, right? So at 80 nanometer, things are easy, right? The way we pattern is there's a single expose. I don't know why I chose purple. There's no significance to it. And then you etch it, and you're done, right? So this is single expose lithography. It takes you down to 80 nanometers. Then we get into this domain of somewhere between 80 and 50, right? So we're now below the single expose cutoff. You can see the wavelength has grown, and here we do this sort of interdigitating, right? We print half the pattern, etch it, print the other half of the pattern, etch that, and then we transfer this all into the wafer substrate. Now, why 50 nanometers, right? I have no sort of really hard scientific number why it's not 40, right? You can do 80 nanometers in a single expose. You do that twice, you should be able to 40 nanometers. The somewhat hand-waving argument is that we become constrained by overlay rather than sort of diffraction limited resolution. It's you could sort of think of it as we can afford to donate about 20% of our critical feature size to overlay. Achieving 5 nanometer alignment accuracy is extremely difficult. So that all adds up to roughly 50 nanometer minimum pitch based on the overlay capabilities of known tools. There are people that do much more sophisticated calculations, and they also come up with 50 nanometers. It's a fairly plus minus a couple of nanometers is a fairly well accepted cutoff in the industry as to the limit of this kind of double patterning technique. Now, we've had a session yesterday on triple patterning, right? So you might say, well, what's the point of introducing a third color? If you can't even get to the fundamental resolution limits with 2 colors, or you can't even get to 40, why are you introducing a third color that in theory should get you to 80 divided by 3, 27 or something, right? And the answer is simply we need that third color to overcome these kind of 2D violations, right? So I'm using my 2 colors, right, green and purple, to resolve the pitch, but now I have line end, tip-to-tip violations that would have to be blown out if I keep them in the same color. So in order to keep a small tip-to-tip space, I introduce a third color, and that basically allows me to close that gap again. So the third color is not a means of getting to smaller pitch. It's simply a means of preserving 2-dimensional scaling. All right, and then from there the process is pretty much the same. Right? Expose, etch, etch. This is why we call it litho etch, litho etch, litho etch, and LE cube is a little bit easier to say. All right, so then how do we get below 50 nanometers, right? So if you want to cover this domain between 50 and 40, and of course there's no law that says you can't introduce these techniques earlier. It's just you can't really extend them further down. So the technique that is being used here, and for obvious reasons, is being called self-aligned double patterning, right? Because it overcomes this misalignment, this overlay dependency on resolution. At IBM, we call it sidewall image transfer because it's historically that's what we had called it for many of the experiments we did probably 20 years ago at this point. And because when we talk about self-aligned double patterning, our managers get very excited. They think now all of a sudden our metal and via is more aligned, and all of a sudden the stack works. But that's not the idea behind the name. But the way this works is you again take half the patterns, you form these what we call mandrel shapes on the wafer. It's basically a relief pattern on the wafer. We then deposit sidewalls onto these mandrel shapes, and every shape has 2 sides, so you've doubled the resolution, right? You cut the frequency in half. You have twice as many patterns on the wafer from what you actually have to do lithographically. A whole bunch of wafer magic happens. And then you come in with a second exposure to add this kind of two-dimensional detail again to your layout, right? It's pretty easy to make gratings with this technique, but if your designers need something more than gratings, you have to work a little bit harder. So this is self-aligned double patterning or sidewall image transfer. And then you have your final image. All right, so that takes us into this domain of double patterning, right? And I gave you a quick overview in cartoons of what this is all about. I thought it might be interesting to kind of distinguish sort of between the first generation of multiple patterning, right? We often do things more than just double patterning, and the second generation. And for us, that's the distinction between the 14 nanometer node and the 10 nanometer node. So we started out with having only a couple of levels that did this litho-etch double patterning technique. And at the time we thought, hey, that was difficult. Things got a lot worse from there. And perhaps more importantly, we managed the cell-to-cell interactions, right? In a sort of standard cell logic design. We were able to come up with some pretty simple boundary conditions so that all the complexity was contained within the cell level design, and there was very little cell-to-cell interaction that had to be color aware, so to speak. Going to the second generation, right, the 10 nanometer node, we have many more levels that now have to be double patterned. We have some levels that are triple patterned for the reasons I just explained, right, that tip to tip we're just running out of space. And we have a few levels that have to go from this fairly simple litho-etch to the self-aligned double patterning. And because the interaction ranges effectively get longer, actually the interaction ranges stay constant as our pitch gets smaller, so more features interact. So now we have to deal with fairly complex cell-to-cell interactions. So all of this, see how we educate designers and design tools to recognize and avoid these things. So unfortunately, there was no discussion on this in the triple patterning session yesterday, but just the idea of how do you report a triple patterning violation back to the designers so that they can do something about it is one of the big open topics that we still have. Another interesting detail, of course, is in extraction, right? With two colors. If you're this center line and you have attackers on the left and the right, those two attackers are the same color because there's only two colors, right? You take up one color, the guys to the left and right have to be the other color, so they're the same color. So they shift together, right? So any kind of overlay error that would translate into a capacitance variation is kind of self-calibrating, right? If space 1 shrinks, space 2 has to increase, and you can take advantage of that in some of the timing calculations. With three colors now, you have multiple choices, right? Your two attackers can be the same color, or your two attackers can be opposite color to each other, which means that now there is no longer a correlation between the two spaces. So I'm not an extraction guy, but I think this is going to take a while for us to resolve. And once we solve it, it really means that these colors have to be fairly permanent in the design, right? You can't time a very sensitive piece of layout based on a certain color combination and then tell the fab, recolor this thing however you want to, right? It's locked in at this point. At least the relative color dependency is locked in at this point. So this again is a problem that is sort of begging to be solved efficiently. Placement is another interesting point. This has really nothing to do with two colors versus three colors. This is simply, as I said, the interaction range between shapes effectively grows. Like I said, it stays fixed, right? It's linked to the wavelength and numerical aperture. But the number of features we're trying to pack into a fixed space is shrinking. So in 14 nanometer, we were able to get away with putting boundary conditions in place so that you could put cells next to each other. The last shape in the cell, the last oh, that's my timer. Huh. So I'll speed up here a little bit. So we were able to put boundary conditions in place to make sure that there is no cell-to-cell interaction. We no longer have this luxury, right? Now the interaction ranges are such, as indicated by these little these connector shapes, that now there is a cell-to-cell interaction, and we have a same color space violation. Fortunately, you know, we have options, right? We have 3 colors available. So one option is to just geometrically flip the cell and hope the conflict goes away, right? Hope you find the other color as you flip the cell. The other, of course, is to do color swapping. And one very promising approach there seems to be to just leave one color frozen and swap the 2 other colors to resolve conflicts. And that, again, would have the side benefit that for extraction purposes, that relative color dependence between your 2 neighbors would be preserved. So I think I have high hopes that this could work. All right, then for routing, right, we started out with litho etch for metal, so the router now had to be 2 color aware. The vias could sort of inherit the colors of the wires, and I'll show you some pictures on that. And now we went to self-aligned double patterning. Things get sort of orders of magnitude more complicated, or interesting, depending on what your sort of perspective on all this is. So this is what we had to do in the first generation of double patterning, where we're working very closely with our EDA partners to teach a router that generating these wiring patterns, they have to be 2 color mappable. For the next generation, right, for SADP, we take this a few steps further. We take one of these colors, build a mandrel mask, deposit the sidewalls, then come back with this block mask, right, this cut mask that I introduced in my cartoons earlier. And then sort of if you squint just right, anything that's not formed by this deposited sidewall and is not covered by the block then forms a metal shape. And I sort of did that Boolean here to show you that we can recreate these patterns. But that introduces a couple of interesting new constraints on our routers. One is the coloring gets a lot more complicated, right? For a litho etch, it's a fairly simple set of rules, right? If you're at minimum space, you have to be opposite color. If you're larger than minimum space, be whatever color dependency you want. For SADP, we still have to be minimum space, opposite color. Then we have a range of forbidden spaces where we have no solution with this deposited sidewall on how to actually make those spaces, so can't design there at all. Then between 3x and 5x space, you have to be the same color because we're going to insert a dummy feature in there that's the opposite color. And then it's not until you get to a 5x space that you can pick the colors however you want. So there's a very, it's a non-monotonic, very complex space. Fortunately, if you do sort of track-based coloring, these rules get a lot easier. The other set of rules that kind of caught us a little bit by surprise in hindsight was this block mask, right? We have to control the physical dimensions of this block mask. We can't have minimum width, minimum space violations. But we don't want to have the router actually generate this block mask, right? That would be sort of too much to ask in the design space. So we have to enforce rules on the metal shapes that guarantee we can make a clean block mask. And that was a good piece of work where we now had to put in these line end stagger rules, right? Where if 2 line ends, I'm showing here on the left, 2 lines facing each other, right? If they're far enough apart, everything is good. Once they start to get closer together, you get a minimum width violation on the block mask. Once they start overlapping a little bit, you have a minimum space violation. And then if they overlap a lot, things are good again. So these rules all had to be captured in design rules and then be translated into routing rules, and we're making very good progress on implementing all of that. The second thing that kind of caught us a little bit by surprise is via coloring, right? Just like all the wires, vias at a space where we cannot resolve them in a single exposure, so we need 2 masks, half the vias on one mask, half the vias on the other, interdigitated, all good. In the first generation of double patterning, the numbers worked out such that once you went across 2 wiring tracks, you could make the vias same color again. So the vias could effectively inherit the color of the wires, right? You spend a lot of effort coloring your wires, you just make the vias the same color as the wire and you're done. We no longer have that luxury now because vias have slightly different resolution requirements than the wires. We now have a situation where even across 2 tracks, same color vias would be a violation. So now the router, in addition to managing the coloring rules and these line and stagger rules, it has to explicitly color the vias and avoid odd cycles, which of course blocks some pin access points. So the whole point of all of this is that double patterning really affects just about every sort of interesting point in the physical design flow. You know, we were talking over lunch. You never really know what problems you run into until you put the whole thing together, right? So we have to work with our EDA partners to put the whole flow together, see what breaks, come up with some excuses why we didn't think of this earlier, and then quickly fix it so that we don't delay tape out of some important chips. Right? And here are some examples of the work with that I've been doing with Cadence, and there's not intended to be any endorsement of Cadence. You know, they're great guys, but within our alliance, we've kind of broken things up that, you know, one partner works with Synopsys, another partner works with Mentor, and I don't know, is it luck or lack thereof, I get to work with Cadence. But here's just some examples, right, that we now see, you know, via coloring coming out of the router that is, you know, good enhancement. We see the line and stagger rules being enforced by the routers. And we've now also started working on, you know, the cell flipping and color swapping to color aware placement. So this doesn't happen overnight. This is probably, I don't know, altogether 6-9 months of really intense work. So, you know, if you want to get into this game, you have to start early, is the message here. All right, so that takes us down to you know, incredibly small resolution, covers us through the 10 nanometer node. But there's more nodes out there, right? And you can see we kind of go into deep black here, you know, very, very critical resolution. What are the plans? Well, one plan is directed self-assembly. Again, there was a paper on directed self-assembly in the triple patterning session yesterday, so it's good to see that it's made it into this conference. But it's sort of the closest to black magic that I ever really want to come. So the idea is now, you know, you can no longer just do frequency doubling, right? So in this case, we take every fourth space, make it a guide pattern. We apply this copolymer film. We heat the thing up, and like magic, that film self-assembles into the feature pitches that we need in our design. And then all that's left to do is come back with a cut mask and add these two-dimensional details, and we're done. And since this all seems a little unbelievable, I thought I'd better show a little bit of background on this. Right, so this idea of block copolymers is that basically you take, you know, a hydrophilic molecule, hydrophobic molecule, oil and water, right? They like to separate, but these evil chemists, they tie them together in the middle, so now they can't separate. They have to sort of self-assemble into low energy states. And depending on the molecular weight ratios that you chose and the thicknesses of these films, they can assemble into different types of patterns. If you make a very thin film of it, you can get these lamella to form, and you know, then you would end up with a pattern that looks sort of surprisingly like fingerprint patterns, right? They perfect pitch, but no orientation. So if you then provide some guide patterns to this, you know, this is the directed part of the self-assembly, right? You provide these guiding patterns. You can actually do you know, 4x pitch multiplication, 6x, I think up to 8x. Things are fairly stable right now. In what Joy Chang, who works at IBM Almaden, who is one of the pioneers of this technique, she called the pitch in a bottle. It's the lithography is sort of secondary at this point. It's all in the chemistry that these films, these block copolymers have to be engineered to give you the right pitch. Here, just another illustration of what I just showed you, and I think, you know, we're running sort of a little bit short on time, and I think you sort of get the idea, right? We provide guide patterns. We put on you know, a lot of surface treatments to get the right energy states. We apply this film, it self-anneals, and it forms these beautiful gratings. You can also do this for vias, right? It's not just a 1D situation where if you have a more interesting guide pattern, you can get via type shapes to self-assemble within these low energy states. I'm still a little skeptical on whether we can actually get the placement of these vias good enough to actually hit the wires at the dimensions we need to do, but there's a lot of very interesting work going on here in directed self-assembly. So it's like I said, kind of, you know, chemistry magic here. Just one demonstration that you can do somewhat useful things with this, right? Here's sort of this undirected film and work we did between IBM Yorktown, Almaden, and some design work out of Carnegie Mellon University, right? If you want to make the fins for a FinFET logic design, the fins might look like this pattern over here. And here's the equivalent fin image formed with directed self-assembly. And you can see, you know, it's a good match. So I think there is some application. You know, in sort of full disclosure, the guiding patterns here were formed with E-beam, so they're very nice and crisp. So that's the next step of making guiding patterns with something with higher throughput. But you know, it looks reasonable. The other approach, of course, is to take this idea of self-aligned double patterning and just do it one more time, right? Do self-aligned quadruple patterning, and you know, conceptually it's pretty straightforward, right? You make a mandrel shape. You deposit sidewalls. You deposit sidewalls onto those sidewalls. Now you've done a 4x multiplication. You have a nice grading, and then you do a cut again. So that conceptually certainly is a little easier to digest than direct self-assembly, but it's still very complicated. So that begs the question of, you know, aren't there any alternatives, right? Do we really want to keep pushing on this K1 factor? And you know, so this is the curve we've been traversing here, 193, right, going through all of these fundamental resolution limits. And then there's this guy up in the corner, right, extreme ultraviolet, which is basically the next wavelength reduction. You're going to X-ray wavelengths. And the history behind this is, as proximity X-ray lithography sort of started to fail, what was it, 20 years ago or so now, some genius renamed the projection X-ray lithography program to extreme ultraviolet, but it's exactly the same thing, right? It's X-ray lithography with a projection lens stuck in there. So, quick update on that, just to convince you that it might be a good idea to at least sort of on a back burner still keep looking at some of these issues. EUV gets this resolution by going to a much shorter wavelength, right? We go from 193 down to 13.5, that's called 14 nanometers. It gives you much better image. The problem is it's all reflective optics, so the numerical aperture is significantly smaller. The initial tools are 0.25, now we're going up to 0.33 numerical aperture. But even though, you know, they chose a name that sounds very similar to Deep UV, right? Deep UV, EUV is supposed to make it sound very evolutionary, very simple. There's not a single critical element in this technology that is at all similar to what we know how to do, right? Everything has to be invented from scratch. They didn't start yesterday. They started sort of 30 years ago at you know, Lawrence Livermore and Big National Labs. So it's a lot of hard work that goes into this, and hopefully we're in sort of the home stretch here, but there's still issues remaining. I haven't changed this slide significantly for the last 5 years, so that's a little scary. But you know, source power is a big concern, right? There's been a big uptick now that 80 watts has been demonstrated at the manufacturer, 50 watts sort of out in the field. We're trying to get to, you know, the initial tools, 80 watts, you know, on our site would be desirable, but ultimately we have to get up to 250 watts to make this whole proposition worth our while. So this is the big challenge. Resist optimization, you know, is very difficult to do when you don't actually have enough light to do these experiments efficiently. And there's a lot of balancing, right? If you make the resist too sensitive, then you get a lot of shot noise, you get very raggedy looking features, you're printing very small images so they have a tendency to fall over. So all of that co-optimization is still ongoing. Image placement is very critical, right? We can make small features, but the alignment system doesn't really benefit at all from this X-ray radiation, right? So that's still a very mechanical system that has to be solved. And then mask defects are a big problem, right? These are very complex masks that are sort of these multi-layer reflectors. At any stage, you can have buried defects in the blank manufacturing. You can have contamination that lands on your mask during exposure, right? There's no protective film. In optical lithography, we have sort of a piece of saran wrap that sits above this mask that we call a pellicle, which, you know, defects land on, but they're outside the focal plane, so they don't matter. We can tolerate that pellicle from getting quite dirty. Here, everything lands directly on the mask and is a problem. So all of that is being addressed in the industry. Up in Albany, at Albany Nanotech, we have this X-ray or EUV Center of Competence. We hope to get to a point where we can run integrated wafers first quarter of next year, and that will really be sort of the first time you know, we really understand what all the secondary problems are that still need to be solved. So again, there is still a huge possibility that for a 7 nanometer node, this won't be ready, and that we have to keep going with other means. So that's that big question mark. We certainly plan to use EUV. We would like to use EUV, but what if it's not ready, right? What do you have to keep going? So I already showed you self-aligned quadruple patterning. I spent an afternoon trying to figure out what design rules for this thing would look like, right? So here's a simple drawing, right? I'm trying to make a couple of wires, say, some power rails and some signal wires. Well, that's pretty easy, right? You make a mandrel shape here, and then you deposit your sidewalls, and in this case, I'm using the second set of sidewalls to form the space between wires, so you're depositing the dielectric. But the thing you run into is that only the red wires are actually lithographically defined. Everything else is derived from these things, right? So if you want to make anything other than a simple grating, like say you want to make a bidirectional kind of wiring layout, well, first of all, you can only go bidirectional on one of these three colors, and it turns exceedingly complicated, right? If you ever get bored, maybe on the plane trying to fly home, the concept is pretty easy, right? Sidewall and sidewall, you do it twice, you're done. But the design constraints, I think anything other than sort of equal line space grading will just be impossible, right? So that leads to the question: can this industry go forward if all we have is gratings, right? Everything else is too complicated. I mean, you can imagine directed self-assembly could work for gratings. Self-aligned quadruple patterning could work for gratings, but can you still do an efficient design? And here we did some work with Carnegie Mellon University. It was sponsored generously by DARPA. And this sort of speaks to this fact of even deeper integration and also opportunities, right? So here's kind of a conventional standard cell. I probably don't have to explain this to this crowd, right? You're looking at first metal in blue, orange are the fins, green is poly. So we have our input pins, our output pin, and some transistors. And here's that same cell rendered in completely unidirectional fashion. So it can be done. You can get the functionality, but there are certain trade-offs. And I'm sorry for rushing through this, but I want to make sure you all get your caffeine and smoke breaks before the sessions start up again. But so if your first metal is completely unidirectional, you still need something to make wiring in the other orientation. So in this case, we're lucky we have our local interconnect level that we can use to make some NFET to PFET connections. But if you use this channel to make that connection with local interconnect, you displace these poly contacts, right? These poly contacts would short to your local interconnect. So now you have to find a different place to contact your poly. So you move some of the poly connections kind of outboard, right, to the edge of the cell. Which means if you make your poly connections out there, you can't run your power rail out there because that space is already taken. So you have to go to inboard power rails, and the whole thing kind of trickles through that. Now you need very robust metal for the power rails, which we don't. You need to have low resistance gate stacks, which are difficult to do. I'll wrap up in the next slide or so. But what this really means is, this can be done, but now it's no longer just design rule engineers and lithographers talking to each other. Now you have to worry about the gate stack, the device architecture, how you bring the power rails into your cells. Can a router deal with the fact that now your second level metal runs perpendicular to the cells, that the power gets dropped into the cells at sort of unpredictable pitches. So all of that requires some very fundamental optimization. This is just speaking to the fact that simple gratings really don't get you very far. You need to have more complex gratings, and I'll skip through this here fairly quickly. Right, the fact that it's good to be able to program in a wider space so that you don't have to trim away dummy fins at these very tight dimensions is very good, and we can do that with directed self-assembly. I already showed some examples of fin pitches. For metal, right, if all you can make is a equal line space grading, your cells kind of suffer because you no longer have wide power rails, your input pins have to be wider and so on. So you get, in this case, 40% reduction in area and power by having some flexibility in your grading. So again, push back to the lithography community that equal line space is not good enough. But the more significant outcome of all of this work was that once you sort of deal with the fact that your layout is very constrained, you can take advantage of it and come up with a very optimized design environment where everything is synthesized. You no longer have sort of custom layout. You have smart memory compilers that can put a little bit of memory in close proximity to a little bit of logic, because layout-wise it all looks the same now. So there are no longer any standoff distances. So this is one piece of work that Carnegie Mellon is working on, is to really leverage the fact that every piece of layout looks identical, because everything is so constrained that you can really get significant improvements in design efficiency. And that takes me to my final slide here, where I hope you sort of enjoyed this walk down memory lane, or the 6 levels of lithography purgatory. And the message I wanted to really get across is that while these achievements are kind of interesting and amazing, the only way we can really get there is by sort of solving all these pieces of the puzzle, right? That patterning can no longer just do this in vacuum, right? You have to understand concerns of the device architecture. Our EDA friends certainly have a word at the table. What kind of cell layouts, cell architectures actually make sense to achieve the design goals. All of this becomes very important. And we manage all of this in a process we now call design technology co-optimization. And I can sort of shamelessly plug my talk that I'm giving at the variability workshop on Thursday, where I'll go into more detail on how we actually within sort of one node manage that piece of the optimization. But for now, I think it's very important to understand that these constraints are becoming more severe. The trade-offs are becoming far less obvious. So early engagement is absolutely vital. And the earlier you're engaged, the more false starts you have. And I know our EDA partners are getting a little frustrated that they develop a lot of good capability and we said, this isn't quite what we needed, and we have to start over again. But that's all part of the technology development. So that's all I have. Thank you very much. I think you all earned your lunch here today.
Okay. Do I have the podium mic? I hate to cut off and invite a talk like this without questions, but we're already over time for getting to the next session. If you would like to learn more about this, it is not too late to sign up for the Thursday workshops. We'd love to see you there on Thursday, and I'm sure Lars will be here between then and now. One small announcement, because of the timing issue, the first afternoon session will be starting 10 minutes past the designated time, so you don't have to immediately have a little time to take a little break between now and then. Okay. We thank our speaker once again, please.